The graph looks normal for a long time. Millions of cosmic rays. Clean separation by energy. A smooth decline exactly where the detector expects it. Then the slope changes. Not sharply. The line simply stops behaving like the same universe that produced the lower energies. Far above the atmosphere, Dampy keeps measuring normally while the high-energy population weakens near the same region, again and again. Nothing disappears. The continuation simply stops extending the way the lower energies did. Dampy measured protons across an enormous range, from roughly 40 giga-electron volts up to 100 tera-electron volts. The detector is still functioning normally. The incoming particles are still arriving. But the distribution no longer spreads the same way. Higher energy should usually mean fewer particles in a predictable spread. Instead, the spectrum begins folding away from its earlier behavior, near the same region where other cosmic ray measurements have shown similar changes. The line keeps descending, but now it looks constrained, as if something invisible started resisting it. A smooth curve begins acting like a limit. The second curve arrives a little later on the screen. Its shape is different at lower energies, but near the far end of the graph, the change begins appearing in almost the same place. Dampy keeps returning to the same high-energy region. Another spectrum is added beside the first one, then another. The lines are not identical. They come from different primary cosmic ray particles, moving through the detector in low Earth orbit. Their populations vary. Their slopes vary. Some fall faster than others. But the weakening keeps reappearing. The comparison stays on screen long enough for the alignment to stop feeling accidental. Each spectrum approaches the tera-electron volt range and begins softening near the same region. Not perfectly, not sharply, just enough to make the earlier bend look less isolated than it did before. The disturbing part is no longer one spectrum by itself. The same behavior keeps returning. Recent DAMP measurements point toward a shared break near 15 tera-electron volts. Researchers still have possible explanations. Local sources could interfere with the distribution. Transport through the galaxy could distort the spectra in similar ways. Statistical effects can sometimes imitate structure for a while. But the graphs continue sitting beside each other, unchanged. Different particles climb toward the same energy region and begin fading under conditions that look uncomfortably similar. A model finally settles over the data cleanly enough to slow the room down. Dampy gives the explanation something solid to fit. The scene shifts away from the detector and into the galaxy itself. A shockwave expands outward from a supernova remnant. Charged particles spiral through tangled magnetic fields, gaining energy as they cross the turbulence again and again. Some escape too early, some collide with interstellar gas. Others simply lose momentum before they can climb further. The process looks inefficient long before it looks impossible. A smooth, broken curve is placed directly over the Dampy measurements. This time, the shape does not feel unnatural. The high-energy softening begins where powerful cosmic accelerators may start reaching their practical limits. Particles become harder to contain, harder to reaccelerate, more likely to leak away before ever reaching Earth. And the overlay fits surprisingly well. Dampy's direct measurements of electrons and positrons, stretching from roughly 25 giga-electron volts up to 4.6 tera-electron volts, are precise enough for the model to settle almost perfectly across the visible spectrum. The mismatch from earlier suddenly looks manageable. The screen stays calm. The model explains why the curves weaken. But the same high-energy region still keeps returning underneath all of it. The fitted curve is still sitting on the screen when another measurement slides into view above it. For a few seconds, the explanation appears to survive. Damp is near Earth, but the break is not local. The detector orbits only a few hundred kilometers above the planet, quietly recording particles before the atmosphere can scatter or absorb them. The source limit model still explains why high-energy spectra should weaken. The curves remain physically believable. Nothing about the mathematics suddenly collapses. But the highlighted energy region does not go away. A new layer appears across the same section of the graph, and the earlier fit starts looking strangely selective. It can explain why particles lose energy. It can explain why acceleration becomes inefficient. What it does not fully absorb is why different primary cosmic ray nuclei continue reacting near the same range. The model still matches the slopes. The high-energy region still refuses to disappear with it. The scene stops focusing on the accelerator itself. The supernova remnants, the magnetic turbulence, the leaking particles, all remain possible parts of the story. But the repeated high-energy region now feels detached from any single source environment, as if the particles are entering a condition larger than the engines that launched them. The answer stays visible on screen while the unresolved region behind it refuses to disappear. The detector keeps orbiting through darkness without changing behavior. Dampy does not see the wall. It sees what fails to cross it. Particle tracks continue entering from deep space. The instrument remains stable. Its measurements continue extending upward through higher and higher energies until the familiar softening appears again. By now, there is a stronger explanation available. A shared propagation limit or universal energy cap could force different cosmic ray particles to weaken near the same range. The idea fits more cleanly than the earlier source models. And still, the final image does not focus on the explanation itself. The graph stretches past the break into a dim continuation where the expected distribution no longer develops normally. The measured spectrum fades. The empty region beyond it becomes easier to notice than the line that still exists. Dampy's high-energy particle program was designed to study cosmic rays and gamma rays at energies human senses could never detect directly. And the detector continues working exactly as intended. Nothing mechanical fails. Nothing shuts down. What matters now is the part of the spectrum that never fully appears. The disturbing part is not the energy itself. It is that higher energy reveals where the spectrum stops continuing normally. The boundary only becomes visible after matter fails to move beyond it. The limit was already there.